So now let's do a quick summary of the kind of work that we're doing with the screws. We've got a couple of options. We talked about there's the upward motion, and an upward motion, well, impending. For upward motion, it doesn't really matter because we're working, we're working against friction. Well, no, not always. But it doesn't really matter how strong friction is because we've got to work against it anyway because it's going to want to naturally roll down. So in this one, our equation is going to look like this, where we've got to work both against the grain of the lead angle, and we have to work against the coefficient of static friction, the friction angle. Then we had two different options for downward impending motion. We had the point where we had a screw that was not self-locking. And in this case, and by that we meant that the theta angle was greater than the friction angle. It wasn't self-locking. So in this case, what we needed to worry about was overcoming the difference between those two angles, but the one was larger. Now, in the other case, we had a screw that was not self-locking. And in this case, the friction angle was greater than theta. And so when we did our derivation, we came up with something like this. And so you can see that these two are very similar. It's just a case of what you're subtracting one from the other versus the other way around. So I think one of the more complicated issues in figuring out how to apply these actually is determining, sounds goofy, whether or not you're looking at downward or upward motion. But once you've determined that, then using the correct equation isn't too rough. Basically, if you do this and you get a minus sign, then you actually had a screw. Oh, sorry, that would have been confusing, right? Then you actually would have got a screw that was self-locking, is self-locking, and we'll go from there.